Welcome, everyone. I'm Sheila Hollis. I'm the Acting Executive Director of the United States Energy Association here in Washington. It's a pleasure to welcome you all today, and particularly to welcome USAID and our NRECA specialists and representatives. The program that you will be listening in on today is one that is clearly at the cutting edge of issues that can have to be contended with, and yet can be a tremendous help in managing the grid, in dealing with CO2 related issues and managing things more effectively and carefully, and adding a layer of technology that would be most helpful to the world and to the United States too. So we're starting today, just on behalf of USEA for a moment. We are a nonprofit, nonpartisan, non-lobbying association. We work very closely with USAID, the State Department, and the Energy Department throughout the world. Been in 104 countries, mainly with USAID over the years. And our hope is to bring clean, affordable, accessible energy to those countries that need it. In addition, we do convening such as this to provide information to the energy industry. Our board is represented on our board are all of the major trade associations in energy in the country. And we have NRECA participation and a variety of nonprofits that participate with us too. We are delighted and honored to have this distinguished panel. I'm always delighted to see Jamila and the rest of our colleagues here today. So welcome, and please take it away, Jamila.
Good morning, good afternoon, good evening. Thank you very much. Always good to be in the panel with you and with our distinguished presenters today. Hello and welcome everybody to our webinar on distribution digital mapping. I'm Jamila Modero, Senior Energy Advisor with the Energy Division within the Center for Environment, Energy and Infrastructure in the Bureau for Democracy, Development and Innovation of USAID. The energy sector, as you know, is undergoing three global trends, transformational trends, also known as 3Ds. First one being digital transformation, which we're learning through these webinar series about, where we learn from utilities that are integrating new tools, digitalization tools for optimization software, grid flexibility, and cloud storage. More recently, we also have been observing a growing trend of decentralization of energy generation, with consumers being able to generate their own energy, storing it and sending it to the grid. Decarbonization is something that I wanted to follow up on what Sheila just said, is something that we have to address, and it's resulting. We promote through our programs integration of renewable energy sources, such as grid scale solar, wind energy, offshore wind, grid, hopefully at some point green hydrogen. It is estimated that in order for us to reach global net zero goals by 2050, we all globally have to increase our spending on infrastructure and associated consumer goods and services by about 60%, reaching 9.2 trillion from the current estimated 5.7 trillion. So this is a huge, heavy lift. But I think today's presentation is a good start for us to look at technology and start thinking in all terms of the 3Ds. And we know that given that the energy sector is a contributor of 2/3 of greenhouse emissions. So we hope to hear from other utilities who are implementing this technology in their programs. And on behalf of USAID, I would like to thank all of you today for participating in this webinar. Also, special thanks to our panelists for joining us today to share their experiences and insights. Special thanks to our USEA leadership and the team for the excellent organization of these webinar series. And without further delay, I'll pass the floor and screen to Jake.
Thank you, Jamila. So good morning, good afternoon, and good evening, everyone. Thank you for attending our fifth webinar in our Grid Modernization series. My name is Jake Swanson, and I'm a senior program coordinator at the U.S. Energy Association, working on our energy utility partnership program in conjunction with USAID. Please note that this webinar is being recorded, and all participants are muted with their video turned off. You're definitely welcome and encouraged to post questions either in the chat or the Q&A box below. I will be monitoring them and passing them on to our presenters as appropriate. You can find past recordings of past webinars on our website at usda.org/EUPP/webinars. So you can watch all of our previous grid modernization webinars as well as our other series in cybersecurity and digitalization. Today's webinar will cover distribution digital mapping, and we have three great speakers today with a lot of expertise in the subject. First off, we have Rakibul Roni, who is the GIS Information Management Specialist in NRECA's project with the Northern Electricity Supply Company, Nesco in Bangladesh. Mr. Roni has 11 years of experience in GIS development, data collection, analysis, and geodatabase development, and he is engaged in data management analysis using a range of different tools in East Africa as well as Colombia. We also have Nicolas Allen, who's the NRECA Director for International Projects. He has a lot of experience leading electrification plans and strategies in the Democratic Republic of Congo, Zambia, Zimbabwe. He's designed and managed numerous electrification initiatives in Ethiopia, Uganda, Malawi, and has led geospatial planning teams in Liberia, Tanzania, Ghana, the Dominican Republic, and Ethiopia. And last but certainly not least is Jessica Williams. She's the supervisor of GIS at Coweta-Fayette EMC in Palmetto, Georgia, in the US. She has 28 years of experience in IT that began when she was enlisted in the Navy. Jessica has led various projects covering GPS data collections and implementation of third-party GIS software. And she's currently leading the implementation of a new outage management system aimed at enhancing outage predictions and managed restoration efforts. So we have a lot of expertise here, and we're excited to hear from them. So with that, I'll pass the floor over to Rakibul and Nicolas.
Great. Hello to everyone. Nicolas Allen with NRECA here. Thank you to USEA and USAID for organizing these events and for inviting us to this particular presentation. We're happy to share some of our expertise, applications, and processes that we follow. Rakibul and I will be leading off this presentation. I'll start and hand over to him. Our presentation is on distribution system digital mapping, as was described by Jake. Basically, we're going to be presenting to you our geospatial framework and processes, and then Rakibul will lead you in an example of how this is applied in a case study on a project we're currently implementing that he's leading in Bangladesh called the Nesco project. So next slide, please. So this is our brief slide on the content. We'll be just giving you an overview of our organization, NRECA International, providing you with some slides on our geospatial planning approach. Then Rakibul will lead you through the case study on how we apply this approach to the Nesco project. And then we'll be turning over to Jessica for her presentation on the Coweta-Fayette Electric Cooperative and how they use GIS and geospatial planning in their system. Next slide, please. A little bit about our organization before we get started. NRECA is the National Rural Electric Cooperative Association. It was formed in 1942 to address common needs of the over 800 electric cooperatives we have today. These electric cooperatives serve many households, businesses throughout the US. NRECA is a trade association, so we cover different needs for our community of electric cooperatives, such as providing financing, insurance, education and training, and advocacy in Washington, DC. We are a dues-based organization, so all the electric cooperatives do pay dues to NRECA to act on their behalf as a trade association. And we have a number of affiliates, as you can see by the different logos at the bottom here, that include insurance companies, finance corporations, and NRECA International, which is where Rakibul and I work. Next slide, please. NRECA International was formed in 1962. We're lucky enough to be one of the first beneficiaries of a cooperative agreement from USAID to begin to provide the expertise NRECA had in helping the electric cooperatives in the US internationally. Today, we've worked in a number of different countries, as can be shown by the green countries shown on the slide. Our work started in Southeast Asia and Latin America, and now is mostly focused on sub-Saharan Africa. We do work a lot with electric cooperatives, but we do work with many different rural utilities, from public sector to private sector utilities, as well as host country ministries and governments in electrification policies and programs, as well as design of different electrification planning approaches. One of the focus areas now is, of course, on geospatial planning. A lot of countries have gone through a least cost planning approach that is based on a geospatial planning tool, some of which we'll be presenting today. Next slide, please. So just to give you a short intro into how NRECA International conducts geospatial planning. Again, this is a planning tool that is not new to the electric utility business. It was done. It's been carried out since the inception, let's say, of an electric utility, but it's mainly been done on paper. The innovation over the last, let's say, 20 to 30 years has been to digitize these paper-based planning approaches into a software platform, what is commonly known as a GIS, or Geographic Information System. So the approach is to take what was typically manually done by electric utility planners and move that into a digital platform to be able to do this at greater scale and more efficiently. Geospatial planning tools can now be used to create not only long-term planning, as is done in many countries, but also on a short-term or medium-term basis, which Jessica will speak to in her system. In our planning tool, we use a database to drive the geospatial planning approach. So this is not only a mapping program, but it's also an integrated database that is relational, so it can connect to other services, other software products, other customer service databases or system databases, engineering platforms as a key example. We use our GIS in conjunction with engineering platforms to conduct load flow studies, other detailed analysis of the system. And we also use it to produce plans, to produce reports. Many of you are familiar with that. And key in terms of geospatial planning is a financial analysis. We use it to connect to our financial analysis model to be able to analyze the cost of projects, either based on a least cost approach or a cost per consumer approach, or looking at NPV of projects. And this allows project beneficiaries, project sponsors, to analyze and prioritize projects based on NPV or other metrics. Next slide, please. So Rakibul will be showing you in the case study how each of those pieces of our approach are integrated into an actual project. Before we turn to that, and probably many of you who are on this call know this, is just to speak briefly about why geospatial platforms are important. And why it's important to not have them be static plans. And I think this is something that Jessica will speak to in her presentation. In our view, a plan on paper is only as good as the day it was printed. As you know, most systems are constantly evolving. So geospatial platforms are databases that are constantly updated. And in order for them to be relevant, not only do they need to be updated and kept, let's say, alive, but they also need to be prepared such that they're not a single-use platform, so they can be connected to other systems. In many developing country contexts, this means connecting them to engineering platform to be able to conduct load flow and voltage drop system on newly planned systems, but also to be able to connect them into policy and to access policy, and how access expansion, both in terms of on-grid and off-grid, is integrated with a geospatial platform with analysis on the cost of projects, prioritization of projects. And all of these are not static, as you know, they all change year to year or even month to month, depending on how quickly a system is evolving. So that's something we view as a key to geospatial platforms, and something I think Rakibul will show you in the example we have. Next slide, please. So I'll now turn this over to Rakibul to take you through the Nesco case study. Rakibul?
Thanks, Nick. Welcome once again, everyone. Good morning, good afternoon, and good evening. Thank you, USEA and USAID for inviting NRECA International in this webinar. You already know I'm Rakibul, the GIS Information Management Specialist. Today, I am going to talk about a case study on an ongoing project, geospatial mapping project in a utility called Nesco. First, let me introduce Nesco with you. Northern Electric Supply Company Limited is one of the 86 distribution utilities of Bangladesh. As you see in the map below, Bangladesh is located in the Southeast Asia, and the Nesco covers almost all urban towns in northwestern part of Bangladesh. It operates 50 sales and distribution divisions. Nesco serves 1.57 million customers. The current distribution lines are about 20,000 kilometers. Nesco is growing very fast. Last 4 financial year, the customer growth rate was 92,000 per year. And at the same time, Nesco spanned about 1,200 kilometers of lines and 456 transformers averagely each year. Two graphs at the right showing the actual number from 2016 to 2017 financial year to 2019-20. Let me give you an overview about the intended outcome of geospatial platform development for Nesco. GIS-based management system will modernize planning, operation, maintenance, and customer services, which will reduce system losses, monitor distribution line outages, and provide a platform for asset management. More specifically, Nesco wants to geolocate all its assets with associated attributes, network load flow analysis in local level offices. Here it's called SND, Service and Distribution Division. GIS-based customer information system, outage management and restoration system, and managing work order. Now let's move to scope and methods of GIS mapping in brief. All components of distribution network have been mapping from primary substation to customer meter. As I showed in my previous slide, about 20,000 kilometers of distribution line, associate pole, substation, transformer, and 1.57 million customers, all will be geolocated with ensuring precise GPS location. The method of GIS mapping started from data review. It's reviewing available data in Nesco to ensure Nesco service area and customer information. Then drone image capturing, which is called UAV image capturing, unnamed aerial vehicle, and extract pole location and customer buildings, building polygons from the images. The next stage is data collection. Separate teams they have deployed for electrical and consumer data collection, but consumer survey follows electrical survey. Then GIS team do the data editing, cleaning, and quality control. And finally, geospatial output are developed with utility asset data, electrical network, digital equipment record card, and consumer locations. Now discuss two key approaches in the geospatial data collection. Approach 1, linking customer to poles. First, along with digital GIS mapping of distribution network, all poles and equipments are assigned a unique number for utility operation. Then customer meter or customer number are linked with the pole from where the service drop are taken. It will give you the answer of the question, who is where? Means utility could able to identify the geolocation of each customer and the part of electric network that customer attach. I would like to put an example from the image here. Customer number here, if you see my mouse, customer number 33001431 is linked with the low voltage pole here. This is called TAL run 211A2. Means it's coming from the substation, 3-digit of substation, 3-digit of feeder name, and the medium voltage pole. And this is, as it is a low voltage network, so it's giving the low voltage feeder name A and B. So we can easily identify this one is coming from the TAL run 211 medium voltage transformer pole, and it can be linked with the substation here. It's Talimari substation and Raninagar feeder. Here is the second key approaches. UAV and or drone images have been capturing for almost full Nesco footprint. First, I would like to point out the steps briefly. The drone image capturing started from making flight plan in the area where Nesco electric line and customer are exist. Then second one is the P-marking ground control points. And the third one is taking the GPS coordinate in the GCPs with the GPS survey. And then taking the UAV image, and image processing and rectification is the next stage with GCPs collected before. And finally, georeference orthomosaic images with the pre-taken GCPs. So it's a higher quality image. The images are below 5 centimeter resolution. You can identify pole clearly, even electric lines. The images are up to date, so no worry about any recent changes in the network. Another driving factor for choosing this technology, because satellite signals degrade in dense urban environment, which is a concern for precise location and time for data capturing with general survey devices. A number of software have been using in different stages of data development. So let's introduce some of the tools here. Input and ODK Collect are Android-based geodata collection apps. Input is similar like QGIS. You can use it in the tablet. Electrical data are collected with input, and the consumer data collected with ODK Collect. WSM End is another Android-based application. It's not directly used in the data collection, but the navigation for the enumerators in the field. Margin, Apache Tomcat, and Aggregate Server, these three are used as online server for data storage, which are coming from the field. Among those three, Margin associate with Input app, and Apache Tomcat and Aggregate Server associate with ODK data collection. Postgres is the relational database for storing, editing, and managing geospatial data in this project. And PostGIS is the database spatial data extender to make the PostgIS for GIS data handling. And finally, QGIS is the desktop GIS software for visualizing, cleaning, and updating the data. All the software here are open source except Margin, which is very low cost for commercial use. Now, I will focus on data collection workflows. First of all, tablet-based data collection. Android tablets are used in field data collection. The data extracted from drone imageries are preloaded in the tablet, and the enumerator visit each pole for filling the attributes. Drop-down choice list, almost full questionnaire is guided with predefined choice list. so no need to write it down in the field, any text. Then yeah, this an application is capable to work offline. After data collection, tablets are synchronized with internet and send the data to online server. Enumerators and in-house GIS personnel use the same database. As it can bidirectional data synchronization capabilities, GIS personnel can push back any concern of the data to the field for field verification. The data quality is checked in both NRECA and Nesco side, and in 3 different stages, the data quality has been checking. NRECA field supervisor in the field, NRECA GIS specialist in-house, and Nesco local officials. Nesco not only involved in the data quality checking, but also in different part of data collection process. Now let's share the geospatial output. This project will give GIS data layers of electrical network with detailed technical and physical attributes. The information is not limited to, but if you see the images, left images here, utility will get substation information, pole with attributes like pole type, materials, fittings, number of feeders in the pole, even the year of installation. For the equipment, equipment type, equipment size, medium voltage and low voltage line details with conductor type, conductor size, etc. And in the middle image showing the unique numbering of each asset and equipment. For equipment, nameplate, maintenance, and physical condition data also available in database. In the image at right shows the information of consumer level. Utility will get each polygon of consumer building, meter or consumer connected pole, and service drop conductor used by the consumer. The whole system is developed with the principle of network analysis, which will give you connectivity and directionality for full electrical network. Now, application of geospatial data. I'm going to share few applications of geospatial data. GIS data will directly convert to ASCII format, which we'll use in windmill for electrical modeling. A complete web tool will be developed for data visualization and also inspection, like asset failing location or vulnerable area identification in the system. Data queries, say for example, joining consumer location with commercial data will give bill collection scenario and the concern area. Quantification, utility asset, which will assist planning. Budgeting, like asset replacement priority list preparation and budget for replacement or renovation. There is another application is the tracing network feature upstream and downstream. Like if a transformer will fail, then utility can identify which part of the network and customer will affect. And the last one is the complaint management system is another application. Let's give you an example. When a customer will call in the customer care, the customer care agent will geolocate the customer immediately and send a push notification for the crew who are responsible for that particular area. Now, I would like to share some challenges when we start this geospatial platform development. Nesco covers mainly urban area. Collecting data is challenging in dense, unplanned urban area. Like in a limited right of way, different service cables are hanging with the electric pole, and sometimes crossing service drop cables over another premises. So it's very difficult for identifying the location of the pole or the connected pole. Need digital conversion of manual record, and sometimes connected differ from this content actually differ from one local office to another. Previous maintenance record may be limited in local offices, and local construction practices are variable. If I want to give you an example, before starting the survey, a full pole fitting list was prepared for using in the form choice list. Non-standard construction need write it down in the text box rather than selecting it from the drop-down list. So it will make your data collection process slower, and sometimes it's confused the data editors for the exact fitting. So it will also applicable for the all other construction also. So interaction with the customer for consumer data collection, this is very complex, and this is the hardest part of data collection. During the survey, some consumer may reluctant to share their data. House may log or owner may not available in the time of survey. So, and sometimes it's a rent house, this is the document bill is not available. So there are many more challenges you will face if you want to do the consumer survey. In this case, you need to do redundant visit of that particular premises or ask direct help from the utility personnel. So lack of updated information also creates some challenges in the field data collection, like the projects which are ongoing or the number of the meter which are replaced may not be available in the central database. So when you go with the database, that may not match with the ground level. Finally, I would like to address the institutionalization of geospatial platform for copying this process and making the database sustainable in Nesco. For maintenance, operation, and future updating, Nesco has been conducting actually NRECA has been conducting several field training for Nesco during data collection and also in-house training. And NRECA involved Nesco officials in the data collection process, showing the purpose of this database and the benefit from the beginning, so that they own their geospatial data and try to involve them in the process. And finally, after finishing this project, all technology and equipment will be transferred to Nesco, so that they can continue the updating work without help of NRECA in future. So that's the end of my presentation. Thank you for your attention. Now I will pass to Jessica Williams, Supervisor of GIS, Coweta-Fayette EMC, Georgia, and she will talk about using GIS tool in her utility. So Jessica, please.
Thank you, Rakibul. Let me get myself shared here. All right. Can everyone see? Am I good here on the video? Oh, wait. Oh, here we go. Okay. So thank you. Good morning, good afternoon, good evening. Thank you everyone for being here. A little bit about myself. So I'm Jessica Williams. I'm the supervisor of GIS at Coweta-Fayette EMC. I started here in 2002, but been in IT and systems now since 1992 when I was in the Navy. Working with the electronic systems helped in my transition to electric distribution. And I shifted to GIS in 2008, and I learned pretty quickly that even though it's databases, there's still a lot more to it than is just databases. In 2010, we, well, let me get over here. So Coweta-Fayette EMC is a member-owned electric utility cooperative that was founded in 1945, located in the southeastern USA. We serve 7 counties in the state of Georgia, just south of Atlanta. Geographically, we're small, but we are the 9th largest cooperative in the state of Georgia. Since we are part of Metro Atlanta, we serve many small businesses, residential, large commercial businesses, and we even have some industrial customers. In our, so I wasn't here when the decision was made to go from paper maps to digital maps, but I am aware of the history. Digital maps were first introduced to Coweta-Fayette in 2002. The paper maps that they had previously used were sent away, digitized, and imported for us to use in a third-party software. And while this expedited the transition from paper to digital, the new maps were only as good as the data that was on the paper map. There was no validating of devices, there was no location accuracy, and there was no attributes for the most part. We conducted a GIS data collection over a span of 26 months, beginning in November of 2011, and we finished roughly at the end of April of 2013. We took this time to do it because it enabled us to spread the cost out over 3 budget years. So we were able to get some in at the end of 2011 using some of that budget year money to spread out that cost. What we got in return is now that all of our employees have access to up-to-date maps, and it's more portable than it was before. So I actually measured and weighed one of the old map books that they used to carry in the trucks, and it was 19 pounds, almost 19 and a half pounds. And it's large. So now they can actually, we started them using laptops, the digital maps are on laptops. Now they're all using iPads, and we have the capability to actually put it on a smartphone. So now there's no more big bulky maps to rely on. With paper map, what you see is what you get. And so this is a portion of one of the old paper maps that we used to have. So you can see where the map cuts off. You have to go find the next page in that big book. If an asset was moved or changed in the field, this was how it was changed. It was just scratched out, or it was redlined in here if it was something new was added to it. These are the consumers, even though there's no symbology to reference, you just kind of have to know what it is. You have limited data that you can put on the map. So like there's wire footage is only available for this particular piece of secondary. There's no member information, there's no pole information. You get limited transformer information. So that's what we dealt with previously. And this is a sample of the same area. It looks a lot cleaner because there's not as much jumble in there, but through the use of labels and attribute tables, there's a whole lot of information that's in there. So the first thing I want to show you is that if we click on this right here, we're able to get information from our the attribute tables that gives us information on our where are we at here? You can find a consumer's name, customer's name and address, phone numbers, whatever information you have available for them. A lot of our information actually comes from our customer information service. But we can see which phase it's being fed on. We can see which feeder it's being fed on. We have different ways to identify that actual location in the field. With poles, we can see construction, how it's built. We can see what type of material it is. We can see what we call a birth year, or how long it's been in the field, when it was last inspected. These units up here actually can tell us how it's built out in the field. So in the instance of a broken pole, from within the office, we can look at this and know what materials to send out with the trucks, and they're not having to come back in and out, not knowing what it is they're actually going out there to fix. This is our transformer information, and you can see we have availability to know the phase code. We can tell which size the bank kVA is, the secondary voltage. Again, this construction unit tells us how it's built on the pole. And we can just keep going here. We can look at our primary conductor. Basically, so what I'm trying to show is that through the attribute tables that are within the GIS data, there's so much more information that you can have in a digital map. These are outdoor lights. And so for us, outdoor lights is a major source of revenue. We can look at and see, we categorize them as yard lights or street lights or parking lot lights. I know some places call them different things, but we know what size of light is out there. We can give a description of where it's located, if it's in the field, or if it's, behind the house, in front of the house, things like that. We can tell through integration with our customer service and customer information system. We know if it's being billed, who it's being billed to, how much it's being charged. And this is all information that's available to our customer service reps as they're speaking to the member. Let's see, another one. So data from all of this systems starts at GIS. So what we, how we use GIS is there's a multiple, it's kind of the center point for a lot of other systems that we have. Some of it is one-way communication from GIS to another system, and some of it is two-way information. So we get information, we send information back and forth. First is our outage management system, or our OMS. And OMS is uses predictive algorithms based on mapped devices and outages reported to show where possible faulted devices are. This keeps the crew from having to guess where to start for looking for their outage sources, and enables the crews to have a starting point for their restoration through the use of smart meters. Can enhance the locating of outages, because those we can initiate a ping and response with those meters, and they'll tell us if they're on or off. The engineering analysis and project planning. So GIS data is imported into these systems to analyze load data. They'll look at the number of and the type of consumers. They'll use transformer KVAs, the per circuit or substation, and this aids in load balancing and forecasting. Just being able to know where things are, locations. They can be integrated with Google or Apple Maps for turn-by-turn directions to non-addressed features. So if we know that we need to send a crew to pole 1, 2, 3, 4, 5, 6, they can actually do a search on pole 1, 2, 3, 4, 5, 6, and it will navigate them to it. With digital maps, now maps are available to employees all throughout the cooperative and to our members as well. Digital maps are more portable, they take up less room, and they're easy to replace. If a device goes bad, you just replace it with a new device. There's no having to rewrite everything for someone. Asset management, this is something that we recently started doing, but asset management allows us to keep up with when a feature was installed or inspected. We can track serial numbers, device specifications, and that sort of thing. Our CIS, or our customer information system, we use that to interface two-way. So we do get customer information into GIS from our CIS, but we also send information back to them. So as far as what the geospatial location is, so that way we can ensure that we're billing the correct taxes and they're in the correct city and county limits when it comes to billing purposes. And now, because those CSRs can see a map, this actually helps them assist in communicating with members, because they now have a bird's eye view of what the member is seeing. We get daily updates to and from GIS. There's constant changes to GIS, and that results in constant changes for end users, including the crews who are carrying those maps with them daily to find out where they need to go, customer service who's talking to members, and there's no need to reprint. So that old bulky book that they could only get it updated once every 6 months or once a year, however it was done, those are actually updated on the daily. And last, we can use staking to design new facilities. So because they know where things are in the map, we know where things are in the field, we can actually design new services and new locations using the GIS data. That new design is actually imported back into GIS, and then whenever it's completed, we post it to the GIS, and then it's available for the crews. And that's one of those, just an example of those daily updates that we get. And those are the ways that we use GIS. I'm sure there's a lot more that can be done, but that's what we use. So thank you for your time, and back to you, Jake.
Great. Thank you so much, Jessica, and Rakibul and Nicolas as well, for your insightful presentations. Let me go ahead and pull up some questions that we got from the audience. So this, I guess these will be open to Jessica as well as Rakibul and Nicolas. One of the questions we got is, can you talk a little bit about the time duration for data mapping and data collection, and exactly how long, or I guess roughly how long these processes can take?
Yes, thank you, Jack. The data collection process is done in 2 phases. So at the initial stage, we did data collection for 5 service and distribution, and the second stage is about 45. So the total duration of data collection about 12 months, though the project duration is about 24 months.
Got it. Thank you for that. And can you talk about a little bit about how digital mapping can specifically help reduce system loss? Either Rakibul, Nicolas, or Jessica.
Yeah, maybe I'll start and then pass it over to each of them. I think Jessica's presentation actually addressed that quite well. She showed the linkage between their GIS and how it's the hub of all their interconnected systems, and particularly the OMS, in terms of relaying information from the existing system, where location-wise and attribute-wise, to be able to either fix repairs when there are severe outages or even minor outages, as well as predictively use that system to be able to monitor system health. And I think Rakibul also talked about a little bit about it from an inception standpoint. When you're first starting out in a geospatial mapping project, identifying all of the elements spatially is a very important thing, especially in planning in systems where there is, let's say, the level of urban planning is not to the degree of what you would find perhaps in Jessica's system, where there are street names and addresses. Finding those locations, having a way to know where a customer is or where a pole is spatially is very important. you can then have more efficient displacement of your work crews. So maybe I'll just open that as a potential way and ask Jessica and Rakibul to add in. Go ahead, Jessica, maybe I'll turn it to you.
Okay, not sure that I'm exactly qualified to answer this question, but as far as system analysis goes, we take the data that we have in GIS and we actually use that, we export that to an external system with our engineering analysis, and then our engineers use that particular software to do the calculating and the load balancing to figure out, where there might be a need for more resources or where we can take resources from if we need it other places.
Great. And Rakibul, anything to add on that, or it's okay if not.
No, I think it's fine. I just give you an example of this study, what we face. If your system is not built very following the standard, sometimes we found the service drop cable is like 100 to 200 meters, even only the service drop cable, and in the periphery of the urban town. So with this data, you can identify the location of the customer and even the length of the service drop cable. So if you find something is not as built or was built according to the standard, you can easily identify this from here.
Great. Thank you, Rakibul. And kind of along those lines, and knowing how GIS, identifies your connections and poles and everything, is it also able to identify if there's an illegal connection happening?
Actually, this is hard part. Actually, what we did, we collect the database, customer database from the utility and try to find out that customer in the ground. So sometimes it could be you may found, or it's not all the customer you will found, but you can find some. I mean, it's not very you could not able to find all of them.
Yeah, go ahead, Jessica.
So when we did our collection, we were able to locate a number of meters that had been illegally placed. They actually were stolen from other utilities nearby and then placed onto our system. Without that actual physical interface between a person's eyes and that actual meter, it's hard to determine if power is being illegally obtained. The use of smart meters helps catch some of that, because if you know that a meter is supposed to be using on an average number of kilowatts per hour, and then suddenly it's using a lot more, it could be that it's been moved to an illegal location, a grow house. We found drug houses that had large power consumption from stolen meters. So there are ways that you can, but it's not necessarily inherent to GIS data, but GIS can be a part of the solution. Right.
That makes sense. And speaking of kind of security concerns, are there any, cybersecurity considerations that you would, take into consideration when undergoing a project like this?
Yes, obviously. Though this is not in my part, our technical part is done by the programmers, and this is obviously a consideration for the cyber security, and in this project, this is also taken into consideration.
One of the things that we rely on.
Thank you, Rock.
One of the things that we rely on is.
No, go ahead, Jessica.
Is there's with GIS, all of your databases can actually be self-contained on in-house servers, which is what we do. We don't do a lot of cloud-based data storage, and we find that helps us to feel more secure in our data that we collect. There is customer information data on the portable devices that the men take out, the crews take out in the field. But through the use of mobile data management software, if one is stolen or lost, that can be remotely connected to and wiped out. So that would take care of protecting that customer information.
Yeah, I'll just add on that we do take cybersecurity very, very seriously. We do end up using a lot of cloud-based databases, mostly because in inverse of what Jessica described, it's very hard for us to find physical servers that have enough speed and internet connectivity to be useful in the field in many of these contexts. So we have to rely on encryption and providing a proper security certificates for all the websites we develop, being very careful with usernames and passwords, et cetera, and what information is publicly held and what information is privately held in our own offline database, let's say. So that's something of importance. I think it has to be counterbalanced against the use of information and accessibility to information to make planning decisions. In a lot of country contexts where we develop these geospatial platforms, I think there is a tendency to go a little bit overboard with protection of information from, let's say, particularly in the off-grid sector, where you're looking to entice developers to develop mini-grid systems, to develop PV farms. These entities need access to information, and the only way to do that is to make it available. If you retain too much because of security concerns, you're also, in a way, kind of stifling the ability for the private sector to play a role. So there is a counterpoint to that. Security is important, particularly on the consumer side, but access to information for planning is typically something that you have to be, have to balance against being overly secure, and allowing people to contribute and view data is important.
Right. And definitely establishing, relationships with, possibly those developers or sometimes even regulators to, keep them in your circle. Those are, some of the people that would be interested in that data and might not be, those are some people that could be in your circle of trust, definitely. And as we all know, that cost is a very important part of any project. Can you kind of give a little bit of a cost estimate as to some of these projects, either Rakibul or Jessica or Nicolas?
Our project was done a number of years ago, so I don't know what the cost estimate, if what I could tell you would be appropriate in today's prices. Like I said, we did stretch it out across 3 budget years so that we were able to ease into that cost that we incurred.
I'll let Rakibul comment on technology costs. There are always, as I think as Rakibul presented, we tend to use a lot of open source technology, which is of course free to use. And we do that specifically so we can turn technology over to a utility or to a host country government or stakeholder without much financial burden to them. Of course, there are commercial products that are quite useful. Our engineering analysis platform is called Windmill. It's developed by a US company that is a paid for service, and they tend to range in, the $15,000 per license area. It's not a cheap tool, and especially when you get into the OMS systems and the AMI systems, it depends on how many meters you're servicing, so they can be quite expensive. I would say, from my experience, the most important investment is, of course, in people. That's where you want to spend money, and good money, hiring good people that can manage these systems, because tools and technologies change a lot. In Rakibul and I's experience, having skilled people who can operate them is of course the key, and keeping them informed, trained, able to use the latest tools is the most important investment any utility or government's going to make. It's the people that really can turn these things, because we can use almost all free tools and create a great product, but we can only do that because we have highly trained people who know how to use them. I'll let Rakibul comment more on it.
Yes, Nick, you are right. I'm not very specific in terms of the resource cost we have, but the total project cost here is $5.1 million for Nesco project. So it has some different part for data collection, data development, even some software development. So that's the whole cost of this project.
And I guess for my last question, because we're just about at the end of the hour, can you talk a little bit about you talked about the cost to the utility, but could you talk a little bit about the potential cost savings of your project?
Yeah. So, yes. Sorry.
Oh, thank you. I'll say for us, what we found is we were able to reduce the number of trips that it took to restore power. We were able to make sure that taxes were being applied properly. We were able to clean up a lot of data that was wrong and that was giving us wrong analysis that we had in the past. We corrected or we located a number of idle services that were just hanging out there, being used as assets that we didn't need anymore. We're still cleaning those up now, and we're 8 years into this. We're still cleaning that kind of stuff up. But we are able to find those idle transformers and those idle locations that we can pull off of the system and reduce our line loss. So there's a lot of different return on investments, if you will, that you'll benefit from once you get all of your data and you start to take a look at it and utilize it.
And Rakibul, did you want to talk about your project as well?
Yes, Jack. Just want to give you an example. As Jessica was telling that now you can where the customers are, the locations, and we are connecting the customer with their numbers. So with the commercial database. So now you can see your commercial return in geographically and the concern area. And if you found something not match with your database, so you can easily identify them. At the same time, you can see where your asset. We also collected the installation year, even which assets are need to replace, and you can do your planning with this actually for this data. And also for operational perspective, so you can do the electrical analysis. You can see where is your which feeders is overloaded and which feeder is underloaded. So you can do your balancing with this data.
Great. Thank you, Rakibul. And thank you to Jessica and Nicolas as well for being here today and presenting. We're so glad that you were able to join us today and share your insights and expertise on this subject. And it's definitely a growing topic of interest, especially under the purview of grid modernization. So thank you again for being here today, and thank you to all of our attendees for joining us as well. I'll be sending out the presentations from today's webinar as well as the recording, so you'll have that to go back to. Yeah, thank you again for joining us, and I hope you have a wonderful rest of the week. So thanks, everyone.